Okay. Can you hear me online? Yes, that's okay. Thank you. Now we'll talk now about elastic collisions. The previous lecture we talked about elastic collisions. We solved, I think, 2 examples, but we can solve more examples also. Now we'll talk about elastic collisions. In elastic collisions, we have the momentum and energy are conserved. Right? And we have 2 relations. One for the moment before and after the collision, and for the kinetic energy before and after the collision. So we have for 2 objects, we have first mass for the object A, for example, multiplied by its velocity before the collision, plus the mass of the object B multiplied by its velocity before the collision is equal to the same mass A multiplied by its velocity after the collision plus the momentum of the second object B after the collision. The velocities are vector in X and Y direction, maybe in Z direction also, Z direction. It's very difficult. Also, we have the kinetic energy. We have almost the same formula shape, but it is for the kinetic energy. The kinetic energy, we know that the kinetic energy formula is different than the momentum by V squared, and we have a half, different than the momentum, plus half mb VB before the collision square is equal to the kinetic energy after the collision. And A after the collision square plus M B after the collision square. In general, in our examples, we gave you the masses and we gave you the velocities before the collision. We have the information before the collision in general. And we ask you to find the velocity after the collision for A or B. Using these relations for inelastic collision, we have 2 unknowns, VA and VB. Just in 1 dimension, but as a vector, V is equal to Vx, I hat, plus Vy, J hat. And if we have the Z direction, we have another component. But to make it simple for us, the most important thing to us is to understand the physical concepts, not to make it difficult as a mathematical problem. Just we don't need to solve equations in mathematics. We need to understand physics, just like that. So we will deal with the velocity just in 1 direction. And if we deal in X direction, it's the same in Y direction and it's the same Z direction. So we will deal with the equations just with the elastic collisions just in 1 dimension, linear motion, maybe in X direction, just like this. Okay. Also, now we have 2 velocities before the collision and 2 velocities after the collision. This will make us deal with 4 components. And sometimes we need to deal with the component or quantity squared, as you see here. This will make the solution be more. I'm sorry, I'm still sick. Okay, the solution for the problem will still long, and it's just mathematics. So we will deal with the velocities before the collision. We just will take one velocity, and we will assume the second object velocity is 0. The object B, we will assume it at rest before the collision. This is the object B, and this is the object A. We'll assume it with 0 velocity. So V will be 0, and this V will be 0. So this term will be 0, and this term will be 0. Before the collision, we have just one term. This will make our solution more simple, and we still can understand the physical constant. This is not trivial. If we deal with object A, move with velocity VA before the collision in x direction. And we have another object B, move with its velocity before the collision in x direction, but in the opposite direction. And we have our coordinate system like this. This is y, and this is x. They will come to collision point, and they will collide, for example, here. Okay, then they will go away. That depends on their masses and their velocities. But our way to solve now, we will take the object B and the object A, and we will assume our coordinate system at B. In this case, VB is equal to 0, and we have just the velocity for A relative to the object B. In this case, we have just one velocity. It's the same. Assume that yourself is standing here. We studied from before the relative velocity. What's the relative velocity for B with respect to you? 0, because you are in the same coordinate system here. In this case, we will solve our formulas more simple. We need to find, in general, the velocity for A after the collision and the velocity for B after the collision. And we assume that they are in just one direction, in x direction. It's okay. In x, this is in x, also this is in x. All of them are in x direction or just in one direction. Any question about that? Online, any question about that? Okay. Now, we need to find VA and VB. We can reorder our equations many times to find VA, in terms of the other variables, and VB the same thing, and we will find that we will not derive them now. The final results are simple to be understood. So we have VA after the collision and VB after the collision. We can find them from these two equations. M will be equal to MA minus MB over MA plus MB multiplied by a velocity VA before the collision. And VB is equal to 2MA over the total mass multiplied by VA before the velocity, the collision. Now, the velocity of the object A after the collision is equal to the mass A minus mass B over the sum of the mass A and B multiplied by a velocity. The denominator here with units kilogram because it's mass minus mass. Also, the denominator is with unit kilogram because it's a mass. Here we have kilogram and we have kilogram. And we have a velocity before the collision. Before the collision, we just have one velocity, which is the velocity for object A. The velocity for object B is 0. There's no velocity. This is meter per second. The kilogram will cancel with the kilogram. Then the velocity after is a velocity, meter per second, but multiplied by some factor. And the velocity for the object B is also the same. It depends on the masses and depend on the velocity for the object A before the collision. Let us now look at a simple example. And all the examples will be simple because the equations are direct to be solved. For example, if we have two objects, A we have object A and object B, and they are moving just in one dimension, in x direction. The mass of A is equal to 2 kilograms. The mass of B, 3 kilograms. This is mass. Okay. Velocity for A before the collision, 3 meters per second in I direction, just in one direction. And the velocity for B is 0. We need just to find the velocity after the collision for each object. So we need to apply these formulas. First of all, we have VA2 is equal to, this is the relation, MA minus MB. MA is 2 minus MB 3 over the summation of them, which is 2 plus 3, multiplied by the velocity of A, which is 3 in I direction. I put the I here just to know something, but we are working in one direction. There's no meaning in general. We are working in I or in J or in K, but I will show you why. This will be equal to minus 1 over, right? Minus 1 multiplied by 3, minus 3 over M5, right? This will be equal to minus 0.6 meter per second in I direction. Now the minus sign in our physics has a meaning. That means A, the object A will reflect its velocity after the collision in the opposite direction. Okay, what about the object B? VB after the collision is equal to 2MA, 2 multiplied by MA, which is 4, over the summation 2, which is 5, multiplied by the velocity again, which is a 3 in I direction. This will be equal to 12, right, over 5, which is equal to 2.4 meter per second in positive I direction. Also, the ball A, it was stationary before the collision. Now it will start move in the positive I direction. Yes. Any question about that? Online, any question about that? Now, we are talking from before that the kinetic energy is conserved. Let us compute the kinetic energy before and after the collision. The velocities that we found now, they guarantee that the kinetic energy is conserved because we found them from before using this relation. So the kinetic energy will be conserved. We will see that now. Okay, kinetic energy before the collision. We can put the summation. Okay, the total kinetic energy. It is equal to the kinetic energy for the particle, the body A before the collision, plus the kinetic energy for the particle B before the collision, which is equal to 1/2 MA VA squared plus 1/2 MB BB squared. This is before the collision. The velocity for B before the collision is 0. So all this term will be 0. This will be equal to half multiplied by the mass of A, which is 2, I think. Right? Right. And the velocity before the collision is 3 squared. Will be equal to 9 joules. Right? This is the kinetic energy before the collision. Let us see now the kinetic energy. I will remove this now. Total kinetic energy after the collision is equal to the kinetic energy for the particle A of the body object A after the collision and the kinetic energy for B after the collision, which is equal now. We don't have any zeros now. So it will be equal to half MA. We know the formulas now. I will apply the numerical values directly. Will be half. The mass of A is 2. The velocity of A, this one, negative 0.6 squared, right? Plus 1/2. The mass 3. The velocity 2.4 squared. This will be equal to the minus squared will be positive. So this will be equal to 2 will cancel 2, 2 will cancel. This will be equal to 0.36 plus I write it here in different way, but it's the same. Okay. because I write this as a 3 over 5, which is the same. Okay, this will be equal to 9 over 25, and this is 12 over 5. It will be the same also. So this will be equal to 1.5 or 25 multiplied by 144. This will be equal all at the end to 9 joules. Okay, the same way. Now we have, see now that the kinetic energy is any question about that? It's the same. I will show you that. This is mathematics test. This is 12 over 5. 12 over 5, which is 2.4. 2 with 3 is 1.5. 12 squared is 144. 5 squared is 25. Just like this. Okay. Now we have special case. We see that many times when we throw a ball or glass ball to another one. The other one is stationary. I'll draw it here. If we have the ball B and the ball A is moving, this is stationary. This is at 0. Now, all of our examples, the ball B is stationary. After the collision, the ball BA will have 0 velocity and ball B start moving. As we see, the ball A give all of its energy to the ball B and all of its velocity. And the ball B takes the place of B in the stationary form. This happens when the mass of A is equal to the mass of B. We write I erase them again. We write the velocity of A after the collision is equal to MA minus MB over MA plus MB because they are equal to each other, then this will be equal to 0. So the velocity will be equal to 0 after the collision of A. And the velocity of B after the collision is equal to 2m A plus MB multiplied by the velocity of A before. But MA is equal to MB, right? They are equal. So we can put this MA. MA plus MA is equal to 2MA. Then we can cancel M with M, 2 with 2. Then VB after is equal to VA before. It will have all the velocity. And the kinetic energy will still be zero. Okay? Now, as a note, when we did our example, mass A now, for our example, when the mass A is equal to 2 and mass B equal to 3, we see that the object A hit B and then reflect because it is lighter than B. But if, for example, A is 5 kilograms and B is 3. When A hits B after that, B will move to the right. Here, B moved this to the right. A. But A will not reflect. It will continue its motion in this direction, but slower. So the effect of B in A will not change the direction of A. It will just reduce its velocity. Do you like example to solve that? See that? Yeah. That's good. Okay. Let us do this example. We did this, and we see that the object A reflects to the opposite side. Now, if we like to, let us give the A velocity 1 meter per second. Okay. So velocity of A after is equal to the change MA minus MB, which is 5 minus 3. That is the formula. Over 5 plus 3 multiplied by 1, which is the velocity. Right? The velocity of A before. This will be equal to 2 over 8, which is a quarter. Which is 0.25 meter per second in I direction, which is positive. But also VB will be equal to 2 multiplied by the mass of A, which is 5, over 5 plus 3 multiplied by the initial velocity of A. This is VB finally, which is 10 over 8. Which is equal to 1.25 meter per second. Also in positive I direction. As you see, when the mass of A is less than B, then A will reflect, right? When the mass of A is equal to B, then A will stop, right? As we see here, the velocity of A after the collision, when they are equal, then the velocity of A, it will not reflect the object A. Is this understood? If the mass of A is bigger than B, then A will continue moving. These are the 3 cases, depending on the mass. Any question about that? I'll move now. Yes. To the center of mass section. When we have any object, for example, this object, if I like to carry it just from one point, if I put my finger here, it will not balance, right? Then I will look for some point to make it stable, right? This point, in general, for this object is called, how can I find it? No, I'm not good in that for this object. But for this object, it will be better, I think, for this rod. Look, I'll put it here. It will not be balanced. If I put it at the center, I think this is cheating. Now I put it at the center of its mass. That means I consider for this object, all of its mass is concentrated just in one point. I can name this point center of mass or a center of gravity or a center of weight of that object. Any mass has its point as a center of mass. Any two masses has a point as a center of mass for both of them. For example, look at this simple example. We have object A and object B. They are separated, not just one mass. The mass of this is 4 kilograms, and the mass of this is 4 kilograms. They are the same. And the distance between their centers is 4 meters. You can tell me easily where is the center of their masses. Where? Because they are identical, the same. You can tell me easily that the center of them is just that geometrical center of their shape, or which is at the point at the middle, which is at 2 meters from here or 2 meters from here. Okay? The center of mass is staying evenly between two masses. What if we have another mass here, C? This mass will pull the center of mass into its direction. To make the new center of mass represent fairly all the masses. I didn't put that in the notes for today. I need to put that, put this note in the next lecture notes, but it's useful to look at the geometrical shapes for geometrical uniform shapes. For example, for a circle, where is the center of mass for it? Yes, sir. For geometrical uniform shape, the center shape, the center of that shape geometrically is the center of mass. This is the center of mass, CM. For a square, it is the intersection between the radial of this one. Okay. For a rectangle, it is the center also. For a triangle, we can. This one. What we have also. For the stick, it is at the middle. For the three-dimensional objects, for example, for a cone, for this cone, you know the cone. It is simple to find that the center of mass is along its axis. But if this is the half of its axis, Do you think the center of mass is below or up? Where is the most of the mass concentrated? Is it below or above? So the center of mass is below or up? It will be below because we have more mass from here. Okay? And to talk more about center of mass, if we have this object, and this object is on the ground, do you think this object will fall down or not? We don't know. But if we look at its center of mass, if its center of mass, what is the name of this line down here? I know it, I forget. If this line, the vertical line downward, is lying within the base, then the center of mass is covered by this object and it will not be fall down. So it will stay. But if we have this object, for example, this is the base and the center of mass is here, it will fall. Because the effect of the center of mass is out of the base. The last point lies here. If the center of mass is here, then it will balance. For example, we have, the humanity, I think, have the Pisa Tower in Italy, if you know it, right? It is not that amount of angle. It's slow, but it is not falling. Why? Because its center of mass lying inside its base. But be sure that when its slope be more and its center of mass vertical effect lie out of the base, it will fall. But that will not happen because the Italian people cover it. Okay. What we have also. Yes. What about this shape? Maybe this shape will not fall because its center of mass not inside it. Because maybe its center of mass outside of this shape. And the effect of this center of mass vertically is within that base. So the center of mass may be located outside the object. For a human, for us, the center of mass is located approximately here. Okay. Then, when we do like this, our center of mass now, because I am not falling down, my center of mass should be located between the area that covered by my foods, right? Like this. And if you are sitting, it is a funny experiment. If you are sitting on a chair, like this, and you try to stand up just like this, you will not be able to do that because your center of mass is located here, for example. And if you are trying to stand up by pushing your legs and downward, your center of mass is staying out of your foot area. But how can you standing up? You should do like this, right? We should change our shape to drag our center of mass, and sometimes we need to make our legs in this shape, right? To drag our center of mass to this point to be covered by our foot. Then we can stand up in a stable way. Any question about center of mass? We will talk about it now by equations. Also, yes, this is the cone is balanced like this, but if we put the cone like this, we know that its center of mass is along this axis, but we are not able to cover it over this point. So it is difficult to make this standing like this, okay? Because its center of mass at 50 centimeters will be out of the base. That's it. Now we are talking about the uniform shapes. What about the non-uniform shapes? I remember that I answered this question when I was in your place. And I feel happy because no one knows this answer but me. We have this shape. No, not this one. I will take this one. How can we know the shape, the center of mass of this shape? It is not uniform. What we can do? Look, if we make this experiment, then the vertical line will pass the center of mass for any object. For this, I will do it now. If I put this is the vertical line, okay? If I do this is the vertical line. If I do this is the vertical line. If I do this is the vertical line. By what is this meaning? What's the meaning of this? By hanging, yes. If we hang any object by hanging the object many times and draw the vertical line, then the vertical lines will intersect in just one point. This point for the non-uniform shapes will be the center of mass. And also it will work for any shapes, for uniform and non-uniform. Okay, now is it understood this point? Now we see that for two objects, mass A and mass B, with different masses, and if they are in an XY plane. So the mass B has the position XB, the mass A has the position XA, and I'll move this to this, and this is has YA, and this has YB. The center of mass will lie on that line that contact their centers. The center of mass, it is at a point on this line. And as a hint, the center of mass is always closest to the heavy object. For example, we have the sun and the air. It's smaller like than this. They have a center of mass. The center of mass is close to the center of the sun. Will not be far away from the center of the sun, because the mass of the earth is very, very small. Okay. Now, if we need to compute the x component of the center of mass, it is simple. X of the center of mass for two objects or more than two is equal to the first mass, for example, multiplied by its x component plus the second mass multiplied by its x component, the position, plus the third mass, for example, multiplied by its x position, plus, and so on. If we have then more 3 or 4 masses, divided over the total mass, which is MA plus MB plus MC plus and so on. This is the x component. We use the x component for each mass. The y component of the center of mass is equal the same, but we will use the y component. MA YA plus MB YB plus MCYC plus so on over MA plus MB plus MC and so on. And the same for Z component, if we like to find it. The denominator here is the total masses, all of the mass of our system. Let us look at this example. We have this plan. We have mass A at 5 and 2. 5 kilograms at 5 and 2. We have the mass B at 0, -6 with 10 kilograms. We have also point C -3 with -3. C, which is 15 kilograms at -3, -3. We need to find the x component of center of mass and the y component of center of mass. We need to use this relation. Now, before we solve it, where do you expect the center of mass will lie? Is it in this direction, or in this direction, or in this direction, or in this direction? We see that the distribution lies in this line. And the most heavy masses in this direction, in the negative y direction. So we will expect that the center of mass will lie in this region, because the heavy objects are here, right? So when you compute and you after you compute your center of mass and you find that your center of mass is here, it is not logical. If you find that your center of mass is here, it is not logical. you need to ask yourself after solving your problem in physics if that result is logical or not. Okay? Because of that, we repeat the solution for the homeworks and the problems many times because sometimes we find illogical results. Now, let me find the x component for the masses. So, x center of mass is equal to, I will apply the numerical values, MA is 5. Any question, by the way? 5 multiplied by its position. How much? 5. Plus B, its mass is 10. And its x component is 0. Plus the mass is 15 for C. And its x component is minus 3. Over the total masses, 5 plus 10 plus 15. This will be equal to 25, 0, minus 45. This will be equal to minus 20 over 30. So it will be equal to minus 2 over. This is x. Maybe our units in meters. Meters, okay? What about the y component of the center of mass? Y is equal. The masses are the same. Look, 5 plus 10 plus 15 over 5 plus 10 plus 15. But what I need to change is just the positions, which are in the y component. For A, it is 2. This is x component. For y is negative 6. This is negative. And negative 3. This will be equal to 10, negative 16, 45 over 30. How much is it? Negative 95. This will be equal to negative 3.16 meters. By the way, this is negative 0.67 meters. Now let us look at the position of our coordinates. In x direction, it is negative 76%. This is a 3, this is 2, this is 1. We are here. Can you see? We are here. Approximately. This is x center of mass. In y direction, it is negative 3.16. This is negative 3. This is 0.16. This is negative 3.16, which is equal to y center of mass. We have the position of center of mass at this point. Is it logical? Are you agree with that? It's good for us. Any question about that? Online, any question about that? Okay. Now, as we know from before that we know about the position vector. The position vector, which is R, is equal to x I hat plus y j hat for anything plus z k hat. Now we have a position vector for a center of mass. We can write R for center of mass is equal to x center of mass I hat plus y center of mass j hat. It is simple. For our example, we find x, we found x, we found y, and we can write the R center of mass for our problem. So in our example, R center of mass is equal to negative over how much? 30. Right? This is the position vector for our system. Now, also, from before, we find that we have a velocity vector, which is the time derivative for the position vector. We know that we have the acceleration vector, which is the time derivative for the velocity vector. Now, if we have, when we compute our system now, this system is at stationary. There is no velocities for the masses. But sometimes we have these systems are moving. Like what? Like a person who is walking on a rope and carrying a stick. There's a center of mass, and he is carrying this stick just to carry his body, and the stick's mass, center of mass, is over the rope to make it balanced. Now, if the center of mass is moving, then it is simple. We can derive the position vector with respect to time. And the derivation will be entered to x component for each one of these terms. This we have, here we have d by dt, here we have d by dt, here also we have d by dt. The mass are constant. Also the same for y. Then this is the velocity. This will be the velocity of the center of mass, which is vx. Vx for the center of mass, it will be equal to the velocities for each object. This is V A in x direction. This is VB in x direction. This is VC in x direction. If we find it in y direction, this is Vy for the center of mass, which is Vy for A. This is VB in y direction also. This is VC in y direction. So the center of mass is moving now. We can find its velocity. Its velocity can be found by finding the center of the velocity for all the masses. What about the acceleration? It is also the same. For example, the acceleration in x direction for center of mass is equal to the mass A multiplied by its acceleration in x direction plus the mass B multiplied by its acceleration in x direction plus and so on over the masses. also the acceleration in y direction for the center of mass is equal to the mass A multiplied by its acceleration in y direction plus mass B multiplied by its acceleration in y direction plus and so on if we have more than two objects and over the masses. Now, from before, we see the x center of mass and y center of mass, and we solve example. Any question about the velocity and acceleration for the center of masses? We just use the velocity in the place of the position and the acceleration in the place of the position. It is just a time derivative. Okay, just like what we used from before for the position, velocity, and acceleration vector. Now we have more than these three vectors: position, velocity, acceleration. What if we multiply by a mass? From where this mass? Which mass is this mass? Is it mass A or B or all of them? Because the center of mass is for all the masses, I need to multiply by all of these masses. It will not be arbitrary application or multiplication. It is just I need to bring this term and multiply it by this. This is MA plus MB plus so on. And also the same here, MA plus MB and so on. I just multiply the both sides by the total mass, which is the denominator here, and I will remove it from here. Can I do that? Huh? I also can name these masses the total mass, which is capital M. Okay, I'll keep it here and here. What about the acceleration? Yes, I can do that. I can multiply the capital M, which is the total mass of our system, by the acceleration, like this. And remove it from here. Okay, now we are physicists. We know what is the meaning of the mass multiplied by the velocity. What is the meaning of that? Aywa? Yes, it's momentum. This is momentum. This is the momentum of all of our system in y direction. This is all of our momentum for our system in x direction. And the same, we can multiply by v, center of mass, in z direction. We can write it by the same way. So, if we have many objects are moving together, they all together have one moment. So, for example, if we have a bicycle, okay, and a bicycle with a person on it, where is the mass is bigger? The second thing, where is the momentum is more? In the second, because we have M1 plus M2. If we multiply them by the velocity, it is the total mass, the total momentum for them. So the momentum for many objects is more than the momentum for one object, plus one object. Okay. Okay. What about the second system of our equations? These equations. M multiplied by A. It's a Newton's second law. It's the force. So the total force applied in our system in x direction, it is M by A, which is MA multiplied by its acceleration, and so on. And the force in y direction applied in our system. If we have many objects, we have 3 objects, and I throw them. I'm sorry for that, but their center of mass is moving uniformly in one trajectory. The force acting on y direction, which is the gravity, it's acting on the center of mass, but the force acting on the first object, the force acting on the first object in y direction, plus the force acting on the second object in y direction, plus the force acting the third object in y direction, all together equal to the total force acting on the whole of our system objects, like this. I can't draw it. I'm looking for this. Okay. And this is the first object. No, this is the trajectory of the center of mass. This is the first object. This is the second object, for example. And for example, this is the third object. And the trajectory of the center of mass is this. It is intermediate between them. And the total forces on them are equal to the total force on this in y direction, and the same in x direction. Let me get this. This is applied in many applications in our life. We will see that example of the rocket. People ask this question. They think they're so smart. They ask, all the experiment outside the Earth is fake. Why that? Because the Newton's third law, we have action and reaction. We know that inside the atmosphere, that the rocket or the plane exhaust hot air backward and can move forward, right? This is a rocket. There is a fire going backward because of the third Newton law. Then the rocket will go forward, right? Right. But what happened? Why this happened? Because we have air layers here, and there is a force on them will push the rocket forward. Okay, what will happen in the outer space? We don't have air in outer space. So what is happening? So this is all of this is fake. That's not right. Because we have momentum. The momentum is conserved. We have in our momentum, we have this is mass A for the rocket, and these exhausted gases has their masses also, and has their velocities. And the rocket has its velocity. So the total momentum should be conserved. The total momentum is the momentum of this plus the momentum of this. And there is no need to the existence of any material here to push ourselves using it. We will see that in the next lecture, solving an exam. Will not be difficult. Okay, what about this? This is the force, as we know from before. This is the force on the center of mass. It will be equal to the time derivative of the momentum of the center of mass, which is this one, with respect to time. Because this is the momentum of the center of mass in any direction, X or Y or Z. This is the momentum of center of mass. In Y direction, it's okay. This is in Y and this is in Y. This is known by us from before that the force is the time derivative of the momentum with respect to time. I'll give you just like this is the last idea about the rocket example. We know that the force is equal to the time derivative to the momentum, which is equal to dm v by dt, right? Always we take m as a constant and take m outside the differentiation, right? And this is the acceleration. Okay? Always we did this. But now in the rocket example, the rocket lose its mass because the exhausted gases, and the gases are going out from the rocket are changing in their mass. So the going out mass is changing, and the rocket is changing its mass. So the mass is not constant in the rocket system. So we cannot put the mass outside that time derivative. So we will put it like this. So the force in our system will be equal d mass by dt multiplied by the velocity plus the mass multiplied by the change in velocity with respect to time. Because the mass is not constant in our system. Okay. There is more example also, which is the belt in the factories. There is a moving belt and carrying, for example, soil or fruit or something, and moving to put it here in to clean them. For example, they are fruit. The motion, the velocity should be constant, but the mass is changing. right? This is another example, but we will not solve it. We just will solve this one. I think we have just the rocket example, and we have to solve. Maybe I will solve another example on inelastic collisions in 2 dimensions when 2 objects come to this direction. This is called inelastic collision, and we are done by this chapter, I think. And that's all for today. And I am sorry again about my case. Any questions in the class, offline? Okay, good luck. Thank you.